Let's look at a gear train where one gear is designated as the driver and the other is considered the follower. So first of all, what makes one gear the driver and the other the follower? Well, gear A here is the driver because it's connected to some external power source. It could be a person just twisting on the shaft of the gear, or it could be a mechanical or electrical power source of some other kind. But the fact is that there's going to be a net torque that's external on A, and then A is going to apply potentially a torque on B through its teeth. And so, first question asks us, what if our gear system was already rotating with an angular speed of omega? Then how much torque does A need to apply on B in order to just keep that angular speed going at constant speed without making it spin faster or slower? So to answer this question, I'm going to draw an analogy here from linear motion. The analogy is a person pushing on box A, and then A in turn pushes on box B. So here, if we want to accelerate box B, then the person needs to push hard enough to exert a force on A, and then A will in turn exert a force on B, causing B to accelerate. And let's assume that there's no friction in this situation. Now what if B were already moving? How hard should the person push on A in order to maintain constant velocity? And so it's a tricky question, but if you understand Newton's first law, then you'll know the answer to this. The answer is the person can't push at all. If they do push, then there would be a net unbalanced force on B, causing it to accelerate. If you want to maintain constant speed, you have to have balanced forces. But there's no force opposing B's motion. Assume no friction and no air resistance. Then all the person can do is just walk with the boxes, but don't apply a force. All right, so hopefully that'll answer the rotational analogy of that. It says, how much torque should A apply on B in order to maintain constant angular velocity? The answer here is 0. A should not exert a torque on B. If it does, it's actually going to angularly accelerate B. But we don't want that. We want constant angular velocity. All right, so that's an example of Newton's first law for rotation. It's just that we want the net torques to be 0 if we want to maintain constant angular velocity. So now let's look at number 2. And in that situation, we actually do want an angular acceleration this time. So let's go ahead and draw the direction of the angular acceleration. It's actually going to be the same for both gears because they have to interlock. Now, what torque does gear A have to apply on gear B in order to achieve this angular acceleration of 1 radian per second squared counterclockwise? First thing we're going to need to note is the moment of inertia of gear B. Okay, so gear B is close to a cylinder in shape. It's not a perfect cylinder or disc, but we're going to treat it as such for the purposes of calculation because it's so close to it. We'll use the formula 1/2 mr squared for that. So his mass is 16 kilograms. radius of 2 meters. That's 32 kilogram meters squared. Now I can use Newton's second law for rotation, which says the net torque on B will equal the moment of inertia of B times the alpha of B. Now that I have the moment of inertia of B, I can plug that in and plug in the desired angular acceleration. Okay. Now what torque is this? It's the net torque on B. But assuming that the shaft of B does not exert a twisting force on B, then the only thing in contact with B that could exert a torque is A. So the net torque on B will be caused by A. That's going to be 32 Newton meters. All right. Now what force from A's teeth causes this 32 Newton meters? Let's take a look at where they're in contact. One of A's teeth can potentially push down on B's tooth with a downward force. We just want to know, how big is that force? It's the force of A on B. Okay, so to calculate it, we're going to use the other formula for torque, which is torque equals Rf. And they told us that the radius of the gear was 2 meters. That's going to be the lever arm of the force, and so that force will be able to cause a counterclockwise torque on B through the lever arm. Let's plug in the desired torque, 32 Newton meters, and then we'll plug in the radius of the gear, and we should be able to solve for that force. So if you solve that, you'll get that the force of A on B must be 16 newtons. Okay, great. Now let's look at a couple other variables here. The tangential speed of the teeth. So in order for the gears to mesh together and lock teeth together, notice that the teeth are the same size. They have to be traveling at the same speed in order to achieve a nice flow of the gears. So these are going to be the same. That's actually true of any interlocking gears, no matter what size they are. Even if you had a big radius gear versus a small one, they still have to have the same tangential speed. Now, what about the arc length, S, traveled by the teeth? Okay, let's assume that that tooth of B makes a full revolution. Hopefully it's clear by the symmetry of the situation and the fact that they have the same tangential speed, that tooth of A is going to come around and meet together with the tooth of B again after they make a revolution. So that distance is called S, and they're the same distance. What about the angular displacement of the gears? Well, we just showed above that one of the teeth made a full revolution. The other tooth made a full revolution too. So these are going to be the same size. Notice though that one of them is counterclockwise, the other is clockwise, they're opposite directions. When it comes to the angular velocity of these gears, they're going to be the same size too. And the angular acceleration, same. Okay, now let's look at some other variables here. How about the force of B on A versus the force of A on B? Well, the answer to that comes from Newton's third law. Newton's third law says that whenever one object exerts a force on another, then there must be a reaction force of that second object on the first, but they would be equal and opposite in direction. So let's see if we can draw that in. Let's draw the reaction force. If A pushes down on B, then B has to push up on A's tooth, just like that. Now how big will be the force of B on A? 16 newtons. Newton's third law always holds true for every force in the universe. But what about this other one, the torque of B on A versus the torque of A on B? There's no Newton's third law for that. They don't actually always have to be equal. In this case, they happen to be equal, but it's only because the gears are the same size. As we'll show in a future video, when you have different size gears, you can create a mechanical advantage and either increase or decrease the torque. But here, because the lever arms are the same length and the forces are the same, it should be clear that they're going to have the same torques. Okay, now let's look at the net torque on each gear. So one thing that's missing from the picture, it's not telling the whole story because it looks like from the picture, A is going to want to angularly accelerate counterclockwise. But we know that that's not going to be the case. A is going to be driving through. It's going to push B down and itself move down as well, the tooth at least. And so it's going to rotate clockwise if it starts from rest. And let's go ahead and draw the one thing that's missing. There must be an external force on that tooth. That could come from a person twisting the gear through its shaft, or perhaps actually physically just pushing on that tooth in the downward direction. But we have to have this external force in order to make A overcome the reaction force of B on A. See, it's resisted by B. We have to overcome that and push through. So the net torques, interestingly, they actually have to be the same. Why do they have to be the same? Because both gears have the same alpha. They have the same angular acceleration. So by Newton's second law, both need the same net torque. But what makes A different from B is that A is attached to that external power source. How much force needs to be applied on the tooth in order to make the diagram correct and complete? Well, 32 newtons. Looks like if somebody pushes on that tooth with 32 newtons, we would subtract 32 minus 16, and then A's tooth would have a 16 newton force in the downward direction, and then it would the diagram would be complete. All right, so finally, the net force on the teeth, it needs to be the same.